In this section, we are going to explore how to compute the derivative of a product and a quotient. Now remember back when we studied limits, there was a limit law that said if we were taking the limit as x approaches a of a function times another function, f times g, we could actually compute the limits separately. So the limit of f of x, essentially, times the limit of g of x. So what happens after we've been studying limits for a while and we switch to derivatives is it's pretty natural to maybe make the assumption that we could do the same thing for derivatives. And that's what we're trying to explore in this section. Is that going to be true? So I have a statement for you here at the beginning asking, is the derivative of f of x times g of x going to be the same as computing the derivative of f of x separately from the derivative of g of x and then multiplying their result? So we want to just try that. Let's try it out and see if that will be true. So let's just choose a monomial for f of x and a monomial for g of x. You can choose any monomial, that's a single term, that you want. I'll just make a few up. Let's say f of x was 3x squared and g of x might be 4x. Those are both monomials. They happen to be power functions, and I'm choosing power functions because we already learned the power rule. So let's go ahead and work through the derivative of f times g. So the derivative of f times g, if we go ahead and input 3x squared for f of x and 4x for g of x, that would mean we would multiply 3x squared times 4x, which will be 12x cubed. And we know how to find the derivative of 12x cubed because we have already learned a few of our shortcuts. We know that we have a constant, multiple, which is the 12, so we'll just take the 12 and then multiply it by the derivative of x cubed. And using the power rule, that's going to be 3x squared. So when we multiply these two, we get 36x squared. So this is the correct answer. This is what we want to get when we are computing the derivative of f times g in this case. So now let's test out our theory or our question at the beginning of, can we take the derivatives separately? So I'm going to go ahead and put a big equal to here with a question mark above it because we're not sure if this is true, and I'm asking that you basically test this out. So can we take the derivative of f of x, compute that, and then multiply it by the derivative of g of x? So let's try it. The derivative of f of x, if f of x is 3x squared, would be, let me actually write that out for you guys, sorry. The derivative of 3x squared times the derivative of g of x, which is 4x. Okay, so the derivative of 3x squared, the 3 is that constant multiple, and then we multiply it by the derivative of x squared, which will be 2x. And then the derivative of 4x, you can do the derivative of 4x two different ways. Remember, we do have a constant multiple, so you could certainly think of the 4 as the constant multiplier. And since this is x to the first power, then if you did use the power rule on that, that's like having 1x to the 0 power. But of course, that's essentially 1. So that's one way to compute the derivative of 4x. But I encourage you to remember that 4x is linear. So if you think of 4x as kind of a linear function, think of it graphically, then the derivative is the slope of that line, and the slope of that line is always 4. So you can do that one two different ways, basically. So we would end up here with essentially 6x times 4, which would give us 24x at the end. Notice we do not get 36x squared like we were thinking we might be able to. So basically what this is showing is you cannot take the derivative of the two functions separately and then multiply those derivatives, because what we're getting here is an incorrect answer. This is the wrong answer. So back to our original question then, is our statement true at the beginning? The answer to this is nope, unfortunately not. We need to develop a separate rule, essentially, that will help us find the derivative of a product. So I'm not going to show the proof in this video. That will be in a separate video. But rather, I'm going to go ahead and show you the product rule and give you some examples of how to use it. So it turns out if we did use the limit definition of the derivative, we could do a formal proof and come up with the product rule. The derivative of f of x times g of x, which will be the first function, f of x, times the derivative of the second function, so that would be times g prime, plus the second function, which is g of x, multiplied by the derivative of the first function, which is f prime of x. Now, remember, this is addition in this rule, so if you were to switch the terms around, of course, that would be fine. So if you wanted to write it as g of x times f prime of x plus f of x times g prime of x, since it's addition, it doesn't matter. I personally remember it the first way, but that's entirely up to you. So here is our product rule. And that's going to help us evaluate derivatives for any two functions that are being multiplied by one another. So let's take a look at examples A and B here, and we will apply the product rule. So our first function, f of x, is equal to the cubed root of x times e to the x power. So first you want to identify where's the product, and we can see our product there. So the two functions being multiplied here are the cube root of x and e to the x. So if it helps to think off to the side as the two individual functions like your f and your g, your f of x function is the cube root of x and your g of x function is e to the x. I'm only labeling these as f and g because in the product rule that we wrote above, we used f and g as our two quantities that are being multiplied. So using the product rule to find f prime, I'm going to go ahead and just write our product rule out here. Remember, it's the first function, f of x, times the derivative of the second function, g prime, plus the second function, g of x, times the derivative of the first function, f prime. So let's start with the first function, f of x, which was the cube root of x. And then we'll be multiplying that by g prime. Well, the derivative of e to the x is just e to the x, plus the second function, the g of x function, which is e to the x, times the derivative of f. Now we do need to think about how to compute the derivative of f, since f is the cube root of x. So it's going to be helpful to rewrite that as x raised to the 1/3 power, because then it's a power function and we can use the power rule. So remember, the power rule basically is saying that we are going to bring that exponent in front. So we'll have a 1/3, and then we're going to subtract 1 from the power. So 1/3 minus 1 will leave us with negative 2/3 as our exponent. So we have successfully used the product rule, and the only thing left to do here is to simplify. And the only simplifying really that I would do would be to factor. So if you can see, we do have two terms here, and there is a greatest common factor. Now, to help you see that, I think it would be wise to rewrite the cube root of x as x to the 1/3 power. And I'm also just going to reorder this second term. I'm going to bring that 1/3 out in front as a coefficient. And then I'm just going to put the x first, just so that I'm writing it in the same order that I wrote the first term. So 1/3 x to the negative 2/3 power times e to the x. So as I look at these two terms, I have a greatest common factor. So we have to analyze each of these separately. So we have x to the 1/3, and then we have x to the negative 2/3. So the greatest common factor there is going to be x to the negative 2/3. Remember, we take the 1 with the smaller exponent. But then we also have a greatest common factor of e to the x in each of these terms. So we will also have e to the x as a part of our GCF. So when you are factoring, remember, we'll have that greatest common factor out here, x to the negative 2/3 times e to the x, and then we're going to write what remains. Now, if it's helpful to you to actually show the division up above here, then go ahead and do that. I'm going to erase my GCF and I'm going to write it underneath each one of my terms, which some of you will go ahead and do the factoring quite easily without writing this down, but if it helps you, by all means, write it down, the little GCF underneath, so you can see the division clearly and not make a careless mistake at this step when you're factoring. So to divide here, we have x to the 1/3 divided by x to the -2/3. So remember, that means we're going to basically be subtracting our exponents. So 1/3 minus -2/3 will be 1/3 plus 2/3, which is really 3/3, which is essentially 1. So that means we're going to have x to the first power, but of course we're not going to write the exponent of a 1. And then the e to the x's completely divide out there. Then we'll have plus 1/3. Here the e to the -2/3 divide out, as well as the e to the x, so we're just left with 1/3. And I can move my parenthesis. It didn't need to be quite as large. So this would be the factored form of the derivative, and this is a great answer. Let me just mention so that you start to be familiar with equivalent forms here. Because there is a negative exponent, this is x to the -2/3, you could also rewrite this by putting the x to the 2/3 in the denominator. Now you're writing this with only positive exponents, and sometimes books or computer programs will prefer that your answer be written with a positive or all positive exponents. So this answer here would be equivalent. Two different ways of writing the same answer. Let's keep going and practice another example here. So example B. And you'll notice I've asked you to do example B 2 different ways, because there are some functions like this one in example B where you have some options. You could certainly use the product rule, but you actually don't have to. This is an example of a problem that you could compute the derivative without using the product rule, because you could do some algebra first and basically distribute, simplify the function first, and then find the derivative. So I'm going to show you both ways so that you can kind of make an educated decision regarding which method you like. So once again, I'm going to go ahead and write our product rule down. So in this case, we're going to find the derivative of our function, which we were calling f. And I'm sorry, these functions were called f. I know it gets a little confusing when you see the product rule and you see that we're using an f here as well, saying the first, times the derivative of the second, plus the second function times the derivative of the first. So if you really don't like that this original function here was called little f of x and you want to change that, maybe you want to change that to like capital H or something like that, that would be totally fine. And maybe that would be less confusing to you when we write down the actual product rule. But that's up to you. So if you want to write this as like capital H of x instead, that would be fine. So let's first identify what two functions are being multiplied together. So hopefully you can see that we have x cubed plus 2 times 4x minus 3. So in this case, it's the x cubed plus 2 that's acting as our first function, f of x, times the g of x function, which is 4x minus 3. So to use the product rule, we'll take that first function, which is the quantity x cubed plus 2, and then we're multiplying it by the derivative of the g of x function. Well, remember, the derivative of 4x will just be 4, and the derivative of the constant is just 0. So the derivative of 4x minus 3 is just 4. Pause for a second, let me say that a different way. Remember, if we were looking at the graph of y equals 4x minus 3, we know this would just be a line, and the slope of that line is always 4. So the other way of thinking about this is to think of it graphically, and that's why the derivative is just 4. Plus the second function, which is the quantity 4x minus 3, times the derivative of the first function. Well, the first function has two terms, so we'll compute the derivative of each term separately. The derivative of x cubed is 3x squared, and once again, the derivative of the constant is just going to be 0. So that will be just 3x squared. So if we want to simplify this, we'll go ahead and distribute. So if we distribute the 4, we'll have 4x cubed plus 8. And then distributing the 3x squared will be 12x cubed minus 9x squared. And combining like terms there looks to give us 16x cubed minus 9x squared plus 8. So that is one way to compute the derivative, that is using the product rule. But again, this is an example of a function where we technically could have done some algebra first. So let me erase all of my marks here. And let's do a little bit of algebra in the beginning. So distributing first really is like us saying, let's do the algebra first, and we'll do the calculus second. So I'm going to go ahead and keep the name of the original function. I'll leave it as h of x, just to be clear. So we're going to actually distribute x cubed plus 2 times 4x minus 3. So distributing x cubed times 4x, we'll have 4x to the 4th power minus 3x to the 3rd power plus 8x minus 6. And it doesn't look like we have any like terms, so we can't really simplify this any further. But by distributing, see what we've accomplished is now we can see that we have 4 individual terms that are being added and subtracted to one another. So we don't need the product rule here. We'll just go ahead and take the derivative of each individual term. So no product rule needed. Let's finish off. Now we can do the calculus and find h prime. So again, derivative of 4x to the 4th, we've got that 4 as our constant multiple. The derivative of x to the 4th will be 4x cubed. And hopefully you're getting faster at doing the power rule now that you've done so many of them. So minus 3 times the derivative of x cubed is 3x squared. Plus, again, there's that 8x term, which is linear. So if you want to just think of it as a line, then the derivative is the slope, and the slope is always 8. And then we have our constant here of 6, and the derivative of a constant will just be 0. So we end up with 16x to the 3rd minus 9x squared plus 8. Thank goodness, because you notice that we get the exact same answer. We just got to it a little different way. So there are going to be some functions, like example A, where there really wasn't any algebra to be done, so we just had to dive into the product rule. And then there are other situations like example B, where you could choose to do the product rule if you wanted to, or you could choose to do some algebra first, and then you wouldn't end up needing to use the product rule.